All right. We're rolling. So, fun little test coming up on Thursday, so any questions? All right.
2016, number 2. It's a really long one, but that's why I think it's a good one because it shows you various topics,
Right, yeah.
when it's disconnected or not connected. So that's fine, yeah.
Okay. All right, so this is, you said 2016?
I think
Number
it's
2.
spring, 2016 spring.
No, summer.
Oh, summer, okay, never mind.
Well, that makes it completely different. All right, so in A, so we have a parallel plate capacitor, ideal, 10 meter by 10 meter plates, 5 centimeters apart, no dielectric, and 20 volt battery. The B, dielectric constant 2.3. C, battery disconnected. D, the distance between the plates is now 10 centimeters. And the dielectric still fills all the space. Find, in each of these scenarios, find the voltage across the plates, capacitance, charge on the plate, the electric field from the plates, and the total electric field. All right. Thank you. All right, remember that when we're dealing with capacitors, we have a couple formulas with which we are dealing. I know that for parallel plate capacitor, I know that the capacitance is equal to kappa epsilon naught A over D. In general, capacitance is Q over delta V. I know that the electric field from the plates is equal to the surface charge density divided by epsilon sub naught. The total electric field would be sigma over epsilon, or alternatively, I guess it's the magnitude. And then we have the VET equation, or the ED equation, and those are magnitudes. And this electric field here is the total. Then we have the two concepts that as long as it's hooked to the battery, the voltage is fixed. And if it is not connected to the battery, the charge is fixed. We are assuming that the disconnection of a battery or anything you do to it does not change the charge on the plates. In other words, no sparking. All right, so the first one, just a straight up, it's hooked to a 20 volt battery, so that's 20 volts. Actually, for part B, it's still hooked to the battery, that's 20 volts. For part C, all we did was disconnect from the battery. We haven't changed anything else, and so that's still 20 volts. But at least after a point, after C, the voltage can change. But just disconnecting the battery does not change the voltage itself, because we haven't changed the charge or anything else. The only thing we've done is just remove the voltage being fixed. Capacitance, well, it's just straight up formula, so that's going to be equal to 1, because there's nothing in between, times epsilon sub naught, usually a decimal point instead of a multiplication symbol there, 8.85 times 10 to the negative 12, times my area, which is 100 square meters, divided by the distance between them, 0.05. that is.
1.77 E to the -8.
And that would be farads. Or 17.7 nanofarads. When we stick the dielectric in between in part B, well, we've increased the capacitance by a factor of 2.3, so it would be this times 2.3 would be here. And apparently I really didn't want to give myself much room. And so that times 2.3.
4.07 e to the -8.
The charge, well, I know the voltage and I know the capacitance, so the charge is just a matter of this second formula right here. That the charge is equal to C delta V. And so just multiply the first two together. Which would be 3.54 times 10 to the -7 coulombs. Now that I know Q, well, I know sigma is the surface charge density, so that's just charge divided by area. So that's Q over A epsilon sub naught. Which would be so I took that out. I'm not doing math in my head real particularly well right now. So C delta V. So it's going to cancel out. And we're left with, so it's 100?
Yeah, 400.
Yeah,
400.
I got 400 also.
But I'm gonna try to do it in my head. So 400 units?
Units per volt per meter.
Either one. And then the total electric field, the only reason that the electric field from the plates and the total electric field would be any different is if there's a dielectric in between. Because the dielectric creates this electric field going in the opposite direction. So since there's nothing in between in part A, it should be the same. Now in part B, when we add the dielectric, we increase the capacitance. In other words, we still have the same voltage between the plates. But since the voltage between the plates stayed the same, but my capacitance increased, one of the purposes of a dielectric, the main purpose of a dielectric, I might claim, then Q is going to have to increase also by a factor of 2.3. So that times 2.3, which is 9 point something.
E to the -8.
Well, which one did you multiply by 2.3?
The capacitance. Primarily, multiplying the capacitance times the voltage. And the difference between that and this is this was multiplied times 2.3 to get here. So it should just be, I multiplied, those two multiplied together. I lied to you, apparently.
Yeah, that one I got 8.14 times 10 to the negative 7.
Which should be that times 2.3.
Yeah,
That's
I
cool.
multiplied that
Yeah.
times 2.3, got the same.
Yeah, okay. Oh. Wow, I am on a roll today. Just trying to make you feel better when you start making careless errors on Thursday. Or make you feel superior when you don't make those careless errors on Thursday. Alright, now I'm back. So we have this charge, this increased charge, and so the electric field from the plates should be increased. Because I have more charge on the plates now. So. .3 or 930.
Got 919.77.
919.77.
I think so.
Okay, it sounds like there's rounding on the involved there. Newtons per coulomb or volt per meter. And the total electric field, well, we go back over here. From this equation right here, from the ed equation, I know that the total electric field, the magnitude of the total electric field, is just the voltage divided by the distance between them. And neither of those have changed. And so the total electric field should be the same as it was before, 400 newtons per coulomb.
So if you were to ask us for the electric field from the dielectric, we could subtract 9.7.
Absolutely. So we can just throw that in there. The electric field from the dielectric magnitude. Dielectric, it would be 0 newtons per coulomb here, and then, I'm just gonna put down 920. And this would be the electric field from the plates and the electric field from the dielectric are in opposite directions. But I put the magnitude symbol around it just to not worry about that.
Okay, and then they're both 400 because the one for B, like the results above are just because of the dielectric there. So
Right.
they would kind of cancel out for that.
For this, yes.
Okay.
Now, in our nice ideal board world, textbook world, we disconnect the battery, what changes? Just by disconnecting the battery, what changes?
The charge is constant, not fixed.
Capacitance would still be the same.
Why?
It's not dependent on those quantities, I guess it's dependent on physical quantities of the capacitor.
Okay. Or you could have also do Q divided by delta V. But the physical quantities here haven't changed at part C. So. All right, so my charge is the same, so what about the electric field from the plates?
What else would be the same?
Yeah, none of those have changed, just by disconnecting the battery. So that's still 920. And then total electric field.
Should be the same.
Yeah, because the dielectric hasn't changed. The charge is still the same. Delta V is the same, D is the same, nothing else has changed.
It's when it gets to D that everything changes, except for the charge.
Yeah. The difference here, when we're going from A to B, because it's hooked to the battery, this has to stay the same. Now we disconnected it, my voltage can change. My charge though will not. So the charge is gonna stay the same for part D, where we just increase the distance and magically fill in the extra space with the dielectric.
we wouldn't know that until we calculate?
Well, we worked through it. If we double the distance, what happens to my capacitance?
It goes down, it's half.
Yeah, so my capacitance is half of what it was. So that's about 2.035. Probably some additional rounding in there somewhere. And voltage is gonna be Q divided by C. So an offshoot of this is that voltage is Q divided by C. Well, C was cut in half, so my voltage doubles.
So if you decrease the distance, the voltage would drop.
Say again?
So if you decrease the distance, the voltage would drop.
Right.
What
If you think about that, if I take two leads of a probe, of a voltmeter, and I touch them to themselves, the voltage is zero.
Mhm.
So as I separate it, it becomes more and more, there's
Right.
more, it takes more energy in order to move from one to the other.
Yeah, that makes sense.
Right, Mario, you were saying?
Yeah, what if we weren't, changing the distance, would the voltage be constant as well?
It comes down to, are we changing anything?
No, nothing at all.
So if my capacitance stays the same, and my charges stay the same, then my voltage has to stay the same.
So we could, theoretically just unplug it and voltage stay the same, and the charge will also be fixed if we don't change any other physical quantity.
Right, theoretically.
Okay.
But again, in reality, when you disconnect, you're probably gonna spark. You'll drain the capacitor or something.
Well, that, and there'd be a function of time in there somewhere.
Yeah,
Oh, that's true. If we're bringing reality into it, there will be
Yeah.
some, especially in the south in the summertime.
That's what I was thinking about, like, wouldn't it like continuously decrease over time since you disconnect?
It would.
Okay.
But we can ignore reality for a little bit. This is a safe space.
Yes. This is physics where you learn to ignore reality.
You bring in a little bit of reality at a time. You know, too much reality all at once and your mind blows, and I don't want that.
That's true.
All right, so in essence, at this point, when we increase the distance, voltage is increased and charge is staying the same. So what about the electric field from the plates? Yeah, as long as I don't increase the distance too much, I still want to stay within that range of close enough to count as infinite plates. So if that stays the same. What about the total electric field?
Yeah.
Because voltage doubled, the distance doubled, so that would stay the same. And therefore that stays the same. So if we compare beginning to end, ultimately the only thing that stayed the same was the total electric field. You good with this?
Definitely, yeah.
Any other questions on this? All right. Other questions at this point?
Yes, I do have a question. It's summer 2020, number 10.
All right, what's the problem?
The current density at one particular cross-section of wire is modeled by J equals 3 amperes per meter squared, then R squared minus 0.5 small r squared. So the other one is big R squared.
This is
Yeah,
big R squared and then little r squared.
yeah, and they're in parentheses. Yeah.
Something like that?
Well, no, it's
No.
the R squared minus 0.5, R squared is in parentheses.
Yeah.
The r squared minus 0.5.
Yeah,
that's,
Well, R squared is in
Yeah.
there, but yeah.
After R squared.
ah. Okay. And I assume capital R is the radius of the wire at that particular moment,
Yes.
and little r is the distance from the center of
Yeah.
central axis. And the question is, what's the current?
Yes.
And general current density is current per cross-sectional area. So if the current density is constant, then we can just get away with its current divided by the, whatever the cross-sectional area of the wire is. However, a little bit of calculus. If it's not constant, then we go to the differential. It's gonna be equal to di dA. And I know that the area of, well, I'm assuming it's a circular cylindrical wire, cross-section would be a circle, so my area is pi r squared. So dA would be 2 pi r dr. There are other ways of coming up with this differential of dA, but that's one of them. So JdA is equal to di, and we're gonna integrate. That's the essence of the problem. I'm gonna ignore units right here. I know that R is gonna be in meters in order for this ultimately to get amperes. Wait a second.
Yeah, that's what
think that's
threw me
right.
off. As well.
Yeah, my units are off there. That's what I wrote down?
Mhm.
So if R is in meters, then this should be actually meters to the fourth power. So then I get amperes per square meter in the end. But I'm going to ignore units. Because I know, ideally, this is in SI units, and so my current should be amperes. Was that the main question that you had?
No,
Okay.
I didn't know.
So integrating 3r squared minus 1.5 little r squared times 2 pi r dr. And so I've got 6 pi big R squared little r minus 3 pi little r cubed dr. I now have it in terms of a single unit, and so I'm going from that central axis to the radius of the wire, so capital R there. And so we do the separate integrals. So it's 6 pi big R squared integral R from 0 to R, dr, minus 3 pi integral R cubed dr from 0 to big R. So 6 pi R squared, and I'm gonna try to write neatly here. 6 pi big R squared, it's little r squared over 2 from 0 to R, minus 3 pi over 4, R to the 4th, 0 to big R. So I end up with 3 pi R to the 4th, minus 3 pi over 4, R to the 4th, which is 2 1/4, 9 pi over 4, R to the 4th.
Can you draw, like, how to visualize it?
All right, so I have current running through a wire. Is that good? Alright, so if we do a cross-sectional area of the wire, then, we'll draw it bigger so I've got some room to draw. So when little r is 0, we have the most amount of current here. The current at the very center would be 3 capital R squared, where this is capital R. As I get further out, when I'm at the side right here, when little r equals big R, my current is less. My current is dropping off as I get closer to the outside here. So in the center, my current density, I guess I should say current density, is 3R squared. That's when the current density is the greatest. At the edge, then my current density is, well, I've got big R squared minus a half of big R squared. So it's becomes 1.5 big R squared. If I did a plot of current density versus little r, see, it's most at the top, it would be something like that. So that's big R. It's supposed to be parabolic in shape. Yep. J versus R, this is big R. Something like that.
I think,
Recognize on the unit issue, the only units coming from here are right here. Those are the units. So the units of this 9 pi over 4 would be amperes per quartic meter. And then this would also be in meters to the 4th power, so they would cancel out and I'm left with amperes in the end.
Do you explain why dA equals 2 pi r dr?
All right, there's 2 ways of looking at that. I know the area, when I'm basically, we have symmetry, cylindrical symmetry about the center. So anywhere along here has the same current density. So my area, it's a circle. My area is pi r squared. My formula has dA in it, so I need to figure out what is the differential of A. And so I just took the derivative of both sides with respect to r. So dA dr is equal to 2 pi r. So dA is 2 pi r dr. A different way of looking at that, because it all depends on how is your mind working at that moment in time. I use the area of this band right here. This has some infinitesimal small, the thickness of that band is dr. dr. And the radius is r. So I can also look at it as in what is the area, what is the infinitesimally small area of that band? Well, if I snip it and I stretch it out, it's a rectangle. So the thickness is dr, so just imagine I have the circle here, I cut it and then I stretch it out. The thickness is dr, and the length is just the circumference of that circle, 2 pi r. So therefore, the differential of the areas length times width. Is that good enough? Other questions? On this one? Other questions?
I have another one.
Okay.
It's just like the probes thing, where to put it to get the maximum resistance and the minimum resistance.
Right.
Is it more of a trial and error, or can you think through it?
You can eliminate some. On some of them, it's a matter of I think is it on that test where all the resistors are the same?
Yeah,
So there's a certain amount that you can eliminate, and a certain amount that you can realize are just the same. Let me do a visual before I try to go off memory on that one. Okay. There was
down.
one down. And then something like that. I even looked at it just so I wouldn't have to go off memory, and it's. Okay. Disconnected up here, and. Thank you. Now, first off, what I drew actually is the exact same circuit. The junction, that's basically a junction right there. Because we're putting all the resistances in the resistor themselves. We're not worrying about the wires, about how much resistance is in the wire itself. So all of that's one junction, all of that is one junction, all of that is one junction. So I basically have three junctions here. There's some symmetry. So putting the probes there will be the same as putting the probes there. So there's a certain amount that you can eliminate without having to try every single possible combination. We can redraw it. Because you've got this end and this end of these parallel structures that are touching, and then at the other end, they're touching the single one. So, again, sort of highlighting the symmetry that's involved there.
So could we calculate, equivalent resistance of, the circuit and then like try to expand it little by little to see which one has the most equivalent resistance?
You could, I think my approach is probably a little bit more brute force, but. So you got around, so I guess you've got all those, putting here, 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 and here would all be the same. Sort of shooting off on my own tangent again, sorry. Your question again, just make sure I answer it.
No, basically I was asking if,